Anand?
No, so like how long will these talks go on for? Like around a semester?
Generally, and for the entire semester, like we have been running this for over a year now. Like this is second
No,
year.
no, not the student talks. I mean, like not the logic webinar.
Okay. The student talks. So I have asked two other people. So apart from you and Ramit, there are two other people who expressed interest, but they haven't responded to my recent email that when would you like to
Oh,
give a talk in September? They said September while filling up the Google form, but did not say anything more. So this is the first time we are doing a student series.
okay. Also, how long has this logic webinar been going on for? I remember at least a year. Or like,
Yeah, so last July we started. July or August? July.
July.
Yeah, last
Yeah.
July we started.
was this still going on like within IITK, like during the basically when? Okay.
Not
No,
really.
so our plan was to start it in IIT Kanpur, and because of the lockdown, everything became online. So therefore, we decided that there are only 4 or 5 people who could attend logic webinars just in the IIT
Right,
Kanpur.
right.
So then instead of a seminar series, we decided to turn it into a webinar series. And now, apart from the two of us, I don't think anybody else attends you regularly. So it has now become an international thing which is attended. Um, I mean, we are getting very few participants these days. I'm not sure about today. Let's hope there are more, uh, because it's after a break. But generally, and like last year, because of lockdown and all, like everybody was so busy attending so many things online that they
Right.
wanted
Yeah.
less screen time and then reduce the time here. It also gets boring after some time to
That is true.
attend. And how did you make this presentation, like in this tree order?
Oh,
LaTeX
so
or
there. No, it's not LaTeX. So there's this thing called Reveal JS. So
okay,
it's these like there are these. It's basically a web-based thing. It's these are HTML slides, not a PDF.
okay.
And so the thing is, I didn't actually manually make these slides. Like you can create a
It's the
markdown file.
template.
No, you can create a markdown file, like just
Okay,
with just the text on the slides, and then you can run a command to generate the slides from them.
okay,
So all I did was to type the contents.
right.
Also, there is a way to switch audio source, right? Like I can't see that option. I usually see it. Oh, audio settings. I guess I'll go there. Can you hear me now?
Yeah.
I have been hearing you.
Okay, so it hasn't changed. I wanted to change it to this. Uh,
Oh,
can you?
that you have to
No, I
click,
can't hear
I
you now.
think.
Uh,
Yeah.
Anand, did you? I mean, do you know about Prathamesh? I guess he also did some type theory, right? Anand. I mean, under Siddharth Gadgil. So, I mean, there are very few people working on type theory in India. Do you know
uh,
that?
uh, yes, Professor Siddhartha Gadgil. Yeah, yes, I have also been working with him during the summer, like as a summer project. Who was the other person you mentioned? I couldn't catch everything because
Prathamesh.
uh,
Prathamesh was his PhD
is,
student, or is, I don't know.
No, working at IIT. He was the postdoc at CAM,
He was a postdoc.
but a postdoc and then to Austria, and now he is
Your
working.
voice is not clear, Purvita.
yeah, yeah, I
Oh,
can't hear.
can you hear me now? Maybe my computer.
It's
It's breaking. It's not
Okay,
consistent.
my internet.
Okay, I can't figure out how to change the microphone, so I let it be.
You can click on the arrow next to the mute button,
Yeah,
and you
it
can
always appears, but
select
this time it hasn't appeared for some
microphone.
reason.
At least one person was trying to join. Where is he? Tefila.
She is also interested to give a talk, but when, that I don't know.
Okay.
I hope you can hear me properly.
Yeah, now it's better.
So when are you coming back, Purvita?
By next week for sure, but when I don't know.
Okay. All these things are being said live on YouTube.
Oh.
Yeah. No, but I can just cut the video, no problem. Don't worry.
Okay. Anil is here.
I don't know.
So it's exactly 7 now. I guess I'll start like maybe in 2 minutes.
Maybe
Or...
we can take 5 more minutes.
Yeah, we should take 5 more minutes so that people join. Hopefully. Have you advertised the talk to your friends?
I mean, I have sent them the link to the Logic webinar thing like long ago when the form was sent out. I haven't advertised this like my talk specifically.
Because there are many new names. I don't know.
Yeah.
Oh, Siddharth is also here.
Yeah, that's great.
Sometime. Yeah. Hi, Anand.
How are you?
Fine, thanks. How are you?
Yeah, we are fine.
Oh, hi. Oh. I didn't notice you were on top. Yeah, Amit. Oh, I guess I've met most people here. Let me enter full screen.
So Anand, how come you have got 2 pointers?
Oh, where? Oh, on my on a presentation.
Yeah.
So I have a complicated setup, and I think like it's showing the pointer twice because of that.
Okay.
Like these are actually 2 separate windows, and I'm trying to merge them into one.
Okay.
So the programming part and the slide one. These are two.
Yeah. I wanted to present them both side by side, without having to switch between each one.
So this is RevealJS on the left, is it?
Yeah.
And the right would be, of course, just Emacs?
VS Code.
Huh?
No, VS Code.
VS Code.
I've just cropped out the border. Yeah.
Yeah, fine. So how do you do this? You just...
I used OBS Studio for this. So like yeah.
Okay. I just switch windows. I won't try these things. Yeah. But it's good if you... It's working out very well. I mean, if you manage it.
Yeah. The thing is, I also wanted to enable speaker view so that I can see the next slide and all that. So
fine.
that's why this thing would be better.
Hello, Amit.
Hello, how are you?
Yes, yeah.
Yeah, hi.
Yes, okay, yeah.
So, actually, we are waiting for some more minutes. Maybe in 2 minutes, Amit, you may start.
Yeah, in 2 minutes we can start. Yeah.
It's 7 o'clock.
Somebody called MJ is trying to enter multiple times but not able to enter.
Maybe some internet issue.
Yeah.
MJ, is that Mahan Maharaj? Mahan is there?
No idea.
I
I
don't know.
have no idea.
Mahan, is that you? Or is there some fake MJ here? Well, there could be other Maharajas also.
Shall we start?
Yeah, I guess.
Yeah,
so.
okay.
Yeah.
Yeah.
So, a very warm welcome to all of you after a long break. We are here for a new session of Logic webinar at IIT Kanpur with a mini series where students and young researchers, they are going to give talks. So the first speaker in our series will be Anand Tadipatri from IISER Pune. He's a 4th year BSMS student in IISER Pune, and he's going to give us take us on a journey to type theory. So
Okay.
over to you, Anand.
Thank you. Yeah, I'll start now. So I'm guessing my slides are already visible. So I'll start. So like Professor Amit mentioned, through this talk, I want to give a glimpse of the field of type theory. And I'll also be introducing a specific variant of type theory, which is the type theory used by Lean. This is known technically as the calculus of inductive constructions, but the name is not necessary over here. So in order to motivate the subject, I was thinking of first giving a brief overview of the history of the subject. So this will sort of illuminate what a type is and why they're important and what kind of features they offer. So just a minute. Yeah. So type theory begins with the work of Bertrand Russell. He was a famous logician responsible for writing the book Principles of Mathematics. So in the year 1901, he uncovered he uncovered a paradox in naive set theory, and this is what we know today as Russell's paradox. I'm guessing this is familiar to most of the people in the audience, so I'll just briefly go through it. So it begins by constructing a specific set, which is the set of all sets that do not contain themselves. Once we have the set, and let's call it R. So once we have the set, if we ask the question, does R contain itself? Then we get a paradox because, yeah, you can derive this quite easily from the definition of R. So this is a paradox in naive set theory. And the obvious problem is declaring this as a set. So logicians want to find a way to avoid declaring this as a set. And there are two main approaches that they adopt. One is to say this sort of expression is not well formed at all. So we cannot have expressions like this. Another approach is to say that this object is well defined, but it's just not a set. So then we can't ask the question whether R belongs to itself anymore, because R, as we've defined it, is comprised of only sets. So we can't ask whether R belongs to itself because R is not a set. So this was the approach adopted by Russell, and he came up with an elaborate framework of types. So the idea is that this structure R over here is somehow a level higher in the hierarchy of things. So we can't ask whether R contains itself anymore because R is built of sets. So that is the main idea. And that's how this paradox of self-reference is avoided. This is one instance. And another instance is with the Lambda calculus. So this is an abstract system of functions invented by Alonzo Church and his colleagues at Princeton. So this has historical significance because Lambda calculus turns out to be equivalent to Turing machines. And there's a lot of history to this. So about Lambda calculus itself, lambda calculus, as I mentioned, it's a theory of functions, and not just any kinds of functions. These are some special kind of abstract functions, which are anonymous. They don't have any sort of name. So a typical lambda expression looks like this. So we write lambda, lowercase lambda, followed by the name of some variable, and we put a full stop and then an expression and an expression m, which may contain x. And so this is how we build a function. We can also apply functions. So if this is another term in the lambda calculus, we can apply it by removing this thing and replacing every instance of x within m with the term that we're applying. So these are very, very similar to actual functions as we see in mathematics. These are just more abstract. They don't have a name. These are very minimal and bare bones, more suited for analyzing their properties and coming up with things like that. So it turns out that this system, in its naive form, where there are no types and any term can be applied to any other term, was actually inconsistent. A number of inconsistencies cropped up eventually. And Church and his colleagues began searching for alternatives to rectify this. So what they came up with is a system called the typed lambda calculus.
Sorry,
Or
Anand,
simply,
can I ask what you meant by inconsistency here? You can prove false or something?
uh, no, so there's this paradox called the Church-Rosser theorem, or
Okay.
Kleene-Rosser theorem, and because of so that turns out to be some sort of an inconsistency within the system.
Okay.
Like you can I think you can, yeah, it's not a proof of false, but it is some sort of inconsistency in the system.
No, I'm puzzled because the lambda calculus is scheme and so on, right? It is used. So,
Yeah, so I think the Y Combinator leads to some sort of paradox of self-reference over there.
okay, fine.
And in practice, I guess Haskell and all those things use like the typed variant of it.
No,
So
Haskell uses, but scheme and Lisps are untyped lambda calculus.
okay,
Okay,
so
I
yeah,
don't need to cite.
yeah, the exact nature of the paradox I'm not aware, but it's called the Kleene-Rosser theorem or Kleene-Rosser paradox.
Sure, thanks.
Yeah. So the solution to this was equipping this lambda calculus with a system of types, like a very simple minimalistic system of types, to ensure that applications and other things are performed consistently and in a way that doesn't lead to paradoxes of any sort. So the basic idea is this. So if you have a term x and you can construct another term e in the context of x, which means that you can construct e by temporarily assuming x, and e has some type tau, then this function over here, the syntax is exactly the same as what we saw on the previous slide. So this function over here has type sigma arrow tau. So the idea is that it's a function from sigma to tau. And this is one way of building functions. We can also destroy functions or apply functions. So that is done in this way. So let's say we have a function f which has type sigma to tau, and you have another term x of type sigma. Then the term f of x, as we would expect, it has type tau. So this is a very simple system of types, and this was a simple framework that was put in place to avoid paradoxes. Uh, the next contribution, a very major one, comes from Martin Löf, and this is sort of an extension of the simply typed lambda calculus that we saw earlier, and also it adds more things. So uh, one major feature of this theory, the Martin Löf type theory, is that it allows something called a dependent type. We'll see what these mean a little later on. But it generalizes the simple types that we saw earlier to something called dependent types. And it also turns out that one can model constructive mathematics within the system. So for this reason, it's also referred to by the name intuitionistic type theory. And because you can perform mathematics within the system, and this was developed around the time where computers were first gaining prominence, a lot of the Martin Löf type theory has been implemented as programming languages several times. So Agda is one. Lean also uses a variant of Martin Löf type theory, and several other systems do that. More recently, a field known as homotopy type theory has come into existence. So this was pioneered by mathematician and fields medalist Vladimir Voivodsky. Uh, So I don't know a lot about this. I won't be talking much about it. But from what I know, uh, this is some sort of a topological interpretation of the Martin law of type theory. So uh, types are interpreted as topological spaces and so on. And this leads to a very nice framework in which a lot of topics in mathematics, such as category theory, can be expressed really naturally. And this is also a very active area of research. And like Martin law of type theory, homotopy type theory has been implemented in several systems. So I guess even in Lean, there's a library of implementing homotopy type theory. So this was the history of the subject. I also want to make some general remarks about type theory itself before proceeding. Uh, Also, from this point on, whenever I say type theory, I mean the type theory that Lean uses. I won't be referring to any other sort of type theory from now on. So there are several variants of it over the years. Each, like even Martinov type theory has several variants, but from now on, I'll be referring only to Lean's type theory. Uh, so sort of to guide our intuition, we can think of type as some sort of a collection of objects that have some common structure. So for example, you can consider the type of natural numbers where everything is a natural number. And because of this, it's similar to a set basically, but with a more rigid structure. So uh, these are also similar to data types in programming languages, if that's a better analogy. Uh, Also, another reason for studying type theory is its relevance for formal theorem proving and the several advantages that it offers. So, as I briefly alluded to earlier, uh, propositions, logical operators, and all these can be expressed within the system of type theory. So that is very powerful. And as a consequence of this, uh, verifying a proof happens to be just a special case of the more general problem of checking the term of a type. So type of a term. So each term has an associated type. We'll get to that soon. So these are advantages of type theory. And another important feature is that type theory allows, so type theory can fill in certain details. It can infer things from the context. And this is more like a practical advantage of it. And it's very useful in the process of writing proofs. So to illustrate these points further, I have a few examples. So in set theory, this is actually a valid statement. So 3 is a topology on 2. This is a side effect of the way things are implemented in set theory. So 1 is actually the set containing the null set, 2 is the set containing 0 and 1, and 3 is the set containing 0, 1, and 2. And because of this, 3 happens to be a valid topology on 2. This is While this is correct, this is not exactly a desirable side effect. We don't like this makes checking hard because we cannot rule out so many things because we can there's no rigid system in which we can categorize things, and it can lead to things like this. This is not desirable basically. And to illustrate the process of type checking, consider this expression over here. So this is a complex expression involving several numbers, but at a glance, you can conclude that the resulting type must be a natural number. This entire expression is actually a natural number, and this can be concluded without actually evaluating this expression. So that's because 1 is a natural number, 3 is a natural number. Basically addition is a map from natural numbers to natural numbers. And by repeated reasoning with exponentiation, multiplication, and so on, this can be seen to have the type natural numbers quite easily without actually evaluating this thing. So the process of checking whether a certain expression is a proof of a certain proposition is analogous to this. By systematically inferring from the lower level details, one can conclude uh, what proposition a certain proof represents. So I'm deliberately being vague now. We'll see this in more detail later on. And so these are the general remarks that I wanted to make. I'll now dive into the formal details of the system. So yeah, yes. Are there any questions? So if not, I'll move on. So now I want to give an overview of the subject, like a more formal one. So we've already seen what loosely what terms and types are and how to think of them. So the basic expressions in the framework of type theory are called terms. And with each term, there's an associated type. And unlike set theory, where a set can belong to multiple sets, in type theory, each term has a specific unique type. So this is in programming, this is the case. Like so, uh, a boolean is a boolean, and like there are no other types associated with it. So that's a general point to keep in mind. And while writing, we use a colon. So this colon is similar to the belongs to symbol that is used in set theory. So x colon t is a formal expression meaning that x is a term that has type t. And here are a few examples. Zero is a natural number, or zero has type natural number, and this expression over here is also a natural number. Okay, and here's a quick detail that I wanted to go through before I proceed. So the lean editor is visible, right? Like I hope all the changes that I'm making are visible now. So uh, here I have a bunch of expressions and I'm checking the type associated with them. So I have zero over here. Lean tells me that this is a natural number. So these are things that it knows because of the way these are implemented internally. True is a Boolean. This expression is also a natural number. And the expression true and false also turns out to be a Boolean. So this is how it works. And as I mentioned, everything is a term and every term has an associated type. So we've seen the natural numbers already. That is a type, but it's also a term of some other type. So if we check natural numbers, I'm not sure why this isn't working. Oh, wait, I think it's working now. Okay, yeah, now it's working. Sorry, I don't know why it's so slow. But yes, natural numbers, which we saw as a type earlier, are actually the term of some other type. And the type is called type itself. So type with a capital T. And we can ask the same question about type. So if we ask Lean what the type of type is, it says type 1. So, and with this, we can expect to see a hierarchy of types. So type 1 has type 2. Sorry, I don't know why it's so slow. And type 2 has type 3 and so on. Like this is a hierarchy and it's not cumulative, which means that natural numbers belong strictly to type and not type 1 or type 2 or any other higher type. So that's a quick comment that I wanted to make because
Sorry, is it an error to say nat colon type 2, for example?
So
Just
nat
check.
colon.
As in homotopy type theory, it is cumulative. Yeah,
Oh, okay.
just check or something.
Okay, I'm not sure how to check, but I remember reading in the Lean manual that in
Okay,
Lean
I
at
mean,
least
I'm
the
sure
types
if you
are
read it,
not
it's
cumulative.
fine.
Okay. So these are the basic types. So, and we can also build new types from existing ones. So the most basic and the most useful one is probably the function type. And I've briefly mentioned these in the context of lambda calculus. I'll mention this again. There are a lot of similarities. So if alpha and beta are certain types, then alpha arrow beta is the represents the type of functions from alpha to beta. So that and like we saw in lambda calculus, if f is a function from alpha to beta and a is a term of type alpha, then f of alpha has type beta as we would expect. So these are obvious details which are exactly the same as we saw in lambda calculus. And these are more technical details that are Lean specific. So the process of actually constructing a function is called abstraction. And it's done in the following way. If we have a term x of type alpha, and we can produce a term t of type beta by temporarily assuming x, then we can construct a function of type x. Basically, we can construct the following function: lambda x t, and this function has the type alpha to beta. So I'll demonstrate this here. So if we have, so yeah, basically, so addition is a function from natural numbers to natural numbers. So I'm sorry. Yeah. So addition is a function that takes in two natural numbers and gives out a single natural number, for example. And so I'll dive into more details of natural numbers here.
যদি যাচ্ছিল ও তো তো
Uh,
বলার পরে বলে যাচ্ছে
so
আমি ভেবেছিলাম যে ওই
so let's say m and n are two natural numbers, or two arbitrary natural numbers, and we have a function f from natural numbers to natural numbers. As we've seen already, we know how to expect this to behave. So f of m is a natural number, f is a function from naturals to naturals. So f of m has type naturals as we expected. Now we want to actually construct a function of function ourselves. So this is an example that I have over here. Uh, so I've written lambda n colon natural numbers n plus 2. So this is actually a function which takes in a number n and adds 2 to it. So it increments it by 2. So this is the syntax of the function. And if we check its type, we see that it has type naturals, arrow naturals. And I'll highlight a few more things about natural numbers over here.
Sorry, simple point is it's lean 4, right?
Yeah, this is lean 4.
Because
Yeah,
syntax
that's why
is
the
different.
implication. Yeah. Yeah. And so here I can construct an example of a function that has the following type. So this arrow is not just between simple types. It can also be between function types. So n to n is the type of all functions from natural numbers to natural numbers. And we can construct an arbitrary function of this type. And how we do that is, so for example, we can temporarily assume a function from naturals to naturals. Now we put an underscore here. Lean tells us what type it expects. It hasn't told me yet. I think it's slow for some reason today. Yeah, but anyway, it will expect a natural number. So I can trivially produce a natural number by evaluating this function at 0. So f of 0 should give me a function without errors. And yeah, it's taking time to sort out everything, but yeah, now it's compiling without errors. I think it's because I have a lot of windows open. But anyway, you can also define functions using the def command when you want to specify their structure, their internal structure. And yes, so this is in a nutshell how functions work. I also want to highlight another important aspect of functions, which is something known as currying. So addition, as we see in regular mathematics, is a function from n cross n to n. So it takes in an ordered pair of numbers and it outputs another number. But in functional programming and lean and n type theory, there are certain advantages to not defining functions this way. In one sense, it's more minimal to define only functions that uh, take in one input at a time. And we'll see how this doesn't actually compromise on generality. So to illustrate this, I've created a few examples over here. So let's assume that we have a function f0, which takes in a pair of natural numbers and gives out another natural number. We want to produce an equivalent function that first takes in a natural number, produces a partially applied function, and then we apply another natural number on that to get the final result that the original function would have produced. So what I do over here is that I use a lambda syntax, lambda n m n. So this is illustrating the type inference that I talked about earlier. Lean can automatically infer what types these are supposed to be. And f0 mn. Sorry, I think I messed up. So lambda m this should work. And similarly, you can construct a function in this partially applied sense. You can take a function of this partially applied kind and produce a proper function from it. So this I will do. Just a minute. So lambda, the syntax might be a bit unintuitive, but the at least the mathematics part, like just a minute. So, but mathematically, it's quite simple. Like what this is doing. yeah, so I'm not sure why. Yeah, okay, this is not giving an error anymore. So this is the addition example is what I wanted to point out earlier. So addition is a function that takes in a natural number, produces another function which takes in another natural number, and then finally gives out the answer. So nat.add2, for example, gives a function which takes in another number and adds 2 to that number. So that's how partial application works. And in Lean, by default, we use partially applied functions. Uh, right. So Lean is taking time. So I'll just move on to the next section. From functions, I want to move on to the subject of logic now. Uh, this may seem like a bit of an abrupt detour, but there is a connection, as we'll see. So more specifically, there is a connection to what's known as constructive logic. This is a system similar to the regular logic, uh, the regular classical logic, but in which proofs are actually constructed, and in which we don't generally use the law of excluded middle. So there are no indirect proofs essentially. Like all proofs are direct, and they produce a proof. So I won't go into the details of constructive logic, but it will be clear through the examples. So first, I want to talk about implication, because this turns out to have a deep connection with functions, as we saw just now. So in implication, let's say we have propositions P and Q, and let's say we also know additionally that the statement P implies Q is true, and we also know that P is true. And from these two facts, we can conclude that Q is true via modus ponens. So this is familiar to everyone via classical logic. And likewise, this is an example of destructing an implication. So to construct an implication, if you can produce a proof of Q uh, by temporarily assuming P, that we have a proof of P, then we can say that we have a proof of P implies Q. So that's how it works. And uh, it, this is actually very similar to what I said a few minutes ago in the context of functions. So in the context of functions, we had similar ways of applying functions instead of using modus ponens, and we had uh, constructing functions or abstracting functions uh, instead of creating implication. But if we look at the core of it, if we look at like a more symbolic description over here, these two notions turn out to be very similar and essentially equivalent. So from a pragmatic point of view, there is no point of separately creating functions and then separately defining implication. Like if one is creating a programming language, it makes more sense to actually identify the two notions and speak of one unified thing, which is both a function and implication. So that's the approach taken by Lean. And so this is essentially what I said more formally and symbolically. And uh, there's a clear parallel between functions and implication. Uh, and so when I say that P is true, uh, what that corresponds to is having a term of type P. So we think of P and Q as two spaces or two types, and we say P has P is a term uh, that has P is basically lowercase p is a term that has type capital P, uh, and this is the same as saying that P is true. So we take that to mean that P is true. So by interpreting things this way, we can construct a correspondence between functions and implication. So I've illustrated modus ponens over here, and over here, this is what's known as a logical axiom that P implies Q implies P. So this is a true statement for all P and Q. So we'll see how to prove this in two contexts. One is the context of uh, propositions, and the other is the context of functions. So like I said earlier, we construct basically we construct a term of type P implies Q by using this lambda syntax. So I write lambda P of type P and I write lambda Q of type Q. And now I need to produce a term of type P. So that will be P itself. So if one type checks this expression, it'll turn out to have type P implies Q implies P. And if we go back to the world of functions, we can repeat the same trick over here. syntactically it looks the same, but it's interpreted differently. So here we have P implies Q implies P. What we need to do is assuming that P and Q are arbitrary types, we need to produce a function having this type. So, or produce a term having this type, more precisely. So what we do is we take an arbitrary element of the type P, and then we now take an arbitrary element of type Q. So Q, and now we need to produce a term that has type P, but we already have one, which is P itself. So we just place that and that works. So syntactically it's the same solution as what I had typed in earlier, but it has a different interpretation in terms of functions instead of propositions. So this can be stated more generally as the Curry-Howard correspondence. So this is a link between what we just saw, which is constructive logic, and type theory, which was first observed by logicians Haskell Curry and William Howard. And so this was first observed for implication in functions, but it turns out to be extend much more generally. This can, for example, be used in the context of proposition for uh, predicates and existential quantifiers and things like that. And it's a very deep correspondence. So usually this is abbreviated as a three-letter word, PAT, which can either stand for propositions as types or equivalently proofs as terms. So each proposition is a data type in itself. That's the interpretation that we just saw. And each term of that type corresponds to a proof. So proof checking is basically term checking in this correspondence by this identification. So that is the main correspondence, and we can extend this to more logical operators. So let's consider conjunction, for example. So uh, constructively speaking, we construct a term of type P and Q by individually providing a proof of both P and Q. Uh, so this is valid in the constructive setting. And does anyone want to guess what the corresponding type version of this will be, like in terms of types? So this is the proposition version. So there's also a type version by the Curry-Howard correspondence. So if anyone has a guess, they can type it in the chat. Uh, um, so it turns out that P and Q corresponds to a product type. So a product type, as I've written over here, uh, is something that takes into product of A and B, product of types A and B, alpha and beta, sorry, takes in first a term of type alpha and then a term of type beta, and produces a term that has basically produces a term of type product alpha beta. And likewise, for and, we have propositions P and Q. We take in a proof of P, we take in a proof of Q, and then we give out a proof of P and Q. So there's a correspondence between products of types and the logical operation of and. So here's an example of how one would construct a term of and PQ. So in the local hypothesis, we assume that P and Q are types. We assume that P is a proof of P, proof of capital P, Q is a proof of capital Q. And now we want to construct a term of type and PQ. So we do and dot intro. Intro is this thing over here. And lowercase p, lowercase q, because these are assumed to be proofs of the respective propositions. And this produces a term of type P and Q. So we interpret this as proving P and Q by assuming P and Q individually. So that was for conjunction. And this can be repeated with other logical operators as well. So for disjunction, the corresponding thing is what would be interpreted set theoretically as a disjoint sum or disjoint union. So in a disjoint sum or disjoint union, we have two sets or types A and B, and we want to construct a term of type A plus B by either using either a term of type A or a term of type B. So that's where the or part comes in, and uh, or works similarly. So if we want to prove P or Q, it suffices to produce either a proof of P or a proof of Q, and then this INL and INR are basically are basically keeping track of uh, which term that we have, which proposition we have proved. We have a proof of basically. If we want to prove P or Q, and we have a proof of P, then this keeps track of that. So uh, compared to classical logic, this is slightly stronger because when we say that we know that P or Q is true, then we are saying that we have a proof of either P or we have a proof of Q. So in this context, it becomes reasonable that the law of excluded middle doesn't hold because, for example, like if we replace P and Q by the Riemann hypothesis, and basically if we take the Riemann hypothesis as an example, we're saying that we either have a proof of the Riemann hypothesis or we don't, or we have a proof that the Riemann hypothesis is false. So this is basically a slightly stronger interpretation of the classical definitions. And at least for me, it seems reasonable in that case to reject the law, basically to not accept the law of excluded middle, because we are saying something stronger over here. Uh, sorry. Um, so to catch a quick glimpse of how sum types work, uh, given A belonging to alpha, I'll try to construct a term of type sum alpha beta. So I have the left proposition basically. I have alpha, but I don't have beta. So I can use INL A, and that should work. Or wait, maybe I should write sum.inl. Sum.inl. I'm sorry. Yeah, so sum.inl A, it compiles. So it's basically saying that I have a term of type sum AB, and I produce it by taking the proof of alpha that I already have and introducing it using the INL uh, constructor. So similarly, in the context of or disjunction, if I have a proof of Q out of P and Q, I have a proof of Q, and I want to produce a proof of P or Q. Now I do or INR. I'm doing INR because I have a proof of Q and not P. So this follows from the constructors. So INR and lowercase q. So this tells Lean that we can construct a term of type P or Q um, using the using the INR constructor, and INR keeps track of where the proof is coming from. So it's not just a black box. Once we say P or Q, we can actually produce uh, either P or Q. So we can keep track of those things. Uh, so another thing is true and false themselves. So these are also types, and true is defined to be a type that has only one constructor. Basically, in set theoretic language, you can interpret this as being a set that has only one element. So it's composed of this thing that we call trivial and nothing else. Trivial is just the name that we've given it. And the corresponding type version of this will be something called unit. Unit is basically a type that contains only one element, which we call star for conventional reasons. So this is the correspondence between types and propositions in this case. And for false, correspondingly, uh, false is something that doesn't have any constructors at all. So over here we had at least one constructor. Over here we have none at all. So false is interpreted as being the empty type or empty set. Basically, there are no terms of type false. So that's the correspondence that we draw. And we can represent these by the symbols top and bottom in LaTeX. And one remaining logical connective is negation. And it turns out that we don't actually define negation in type theory explicitly. We just treat it as some sort of a shorthand. So specifically, we say negation P for a proposition P is shorthand for P implies false. So in classical logic, these are equivalent. And in constructive logic, this is saying that we can produce a function that takes a term of type P and produces a term of type false. So that's what we're saying when we mean negation P in the context of constructive logic. And uh, yeah, so it's basically a function. And over here, I will do a quick proof of contraposition. So if we assume that we have P implies Q, we need to show that not P implies not Q. So we can do that by first assuming that we have a term of type not Q. Basically, this is a function that takes a term of type Q and produces false. So we assume that we have a function of not Q, not Q, and now we are left to, so to complete this construction, uh, we need to produce a term of type not P. And not P is an abbreviation for a function that takes a term of type P and produces false. So we take a term, we assume a term P of type capital P. And now we're left with proving false, as Lean will tell us. Yeah, we need to prove false now. And to prove false, uh, what we have in our local context is a function which takes in a term of type Q and produces a term of type false. So if we can somehow use that, the idea is to somehow use that, and to produce a term of type Q, we can use the term of, we can use the function f that we have. It takes in a term, takes in P and it outputs Q, and for that we need a term of type P, but we already have one by assumption, which is lowercase p. So I would write this as the nq is a function that takes in a term of type q and produces false. So nq applied to f applied to p. So that summarizes the argument that I just made. So this takes q and produces false. This takes p and produces q, and by composing them together, we have a function that takes in, that produces false. Basically, we have a proof of false in this local context. So we haven't proved false actually. Yeah. So that, yeah, that's how negation works in this context. And so uh, this section I'd like to conclude with some details about the type prop that we've been working in. So over here I've written prop in several places, and prop is actually a type, a universe actually. A universe is basically a type that contains other types. So prop is basically taken to be the universe of propositions, and this has a few unique features that in the lean implementation of it. So one property is the fact of proof irrelevance, which means that if you have p of type capital P and p dash of type capital P, then p and p dash are essentially the same. It doesn't matter which proof that you which proof you use in uh, which proof of p you use in constructions. And another thing is impredicativity. This is more a technical condition, and from what I understand, it says that if you have a function which takes in, basically if you have a function from an arbitrary type to prop, then the resulting function has type prop as opposed to a higher type. So if you have a function between some type of type u and a function between and which takes it to a type of type v, then the resulting function will have type of maximum u plus v, or maximum u and v. So, but this is not the case with prop. Uh, and this is because we want to express propositions like for all n, this holds n, and things like that. And we want that to be considered as a proposition. So that's what I understand by impredicativity, but it's more of a technical condition which doesn't show up in practice a lot. So now we've seen functions and we've seen uh, the connection with logic. And what I said earlier about the Martin-Löf type theory is that it introduces something called a dependent function type. So these are functions in which the output type can depend on the input. So as a motivation, we can consider this problem. So let's say we want to construct a function which first takes in a natural number and then outputs a list containing the first n natural numbers in some order. Uh, and we also want to encode this information in the type of the function itself. So normally, like in simple type theory, we would probably have a function of type n goes to list of natural numbers. We're saying the input is a natural number, and we're saying the output is some list of natural numbers. But in addition to this, we want to encode further that the output has a certain size, which depends on the input. So what we want to say in the type signature of this is that we want to express the fact that it's a function that takes in a natural number and outputs a vector of size n, where n is the input. So this is something that cannot be done in the regular theory of typed functions, but it can be done in a more general setting, which is a setting of dependent types. So, sorry, yeah. So dependent types. So this is basically a function that takes in a natural number and outputs a vector of natural numbers of size n. So these sort of constructions are possible only in the theory of dependent types. And how this is constructed is not very relevant. So basically, for 0, it returns an empty vector. And for n plus 1, it just appends the number n to the previous one. So it's defined recursively. So f of n is the previous one. And f of 5, for instance, is this thing over here, 4, 3, 2, 1, 0, and the empty list. And that if we want to check the type of f, we see that it has a desired type. It takes in a natural number n and outputs a vector of natural numbers of the required size. So we're able to capture these higher order details by generalizing our functions to dependent types. So I'll define dependent types in a moment. So So dependent types are actually not too different from the regular function types. These are constructed in more or less the same way, except there's the additional thing that the type of the output does not have to stay constant. So if we have a term of if we have a term A of type alpha, and we by locally assuming its existence, we can construct a term T of type beta alpha, where this type itself depends on the input A. Sorry, this should have been beta A. So basically the type depends on the input. If we can do this sort of thing, then dependent type theory allows us to construct a function which is lambda a goes to t, which has a type this thing over here. We're choosing a specific a belonging to alpha, and we're producing a term of type beta a. Beta a is a term that depends on a. And so these are generalizations of functions. The output, basically, as I mentioned, can vary with the input. The type of the output can vary with the input. And since regular functions are only a special case of this, Lean implements regular functions as special cases of dependent function types. And like how we saw the connection between regular function types and propositional logic, we'll see a connection soon between dependent types and the predicates and quantifiers and so on. So the first thing is universal quantifier. So if you want to say for all x something happens, what we are considering actually is a dependent. So the type version of it will be a dependent type, which takes a term x of type alpha and produces a term px which has the type prop. So we're basically producing a proposition. We're producing a different proposition for every input x, and each proposition is a new type in itself. So basically, what we want to convey is that for every x in alpha, p of x holds, and this we think of just as how we thought of just as how we thought of the implication as a function. We'll think of uh, quantification, universal quantification, as a dependent function. So if we have something like this, the statement of Fermat's last theorem, it takes in a natural number n, and corresponding to that n, it produces a type. This entire thing is a type that depends on n. So that is how universal quantifiers behave. And the Curry-Howard correspondence applies here as well. On one hand, we have universal quantification, and on the other hand, we have dependent function types, which are also called dependent products. So the reason these are called dependent products will be clear, because there are also dependent sums. which correspond to existential quantifiers. So existential quantifiers behave slightly differently. Uh, basically, yeah, basically, what we are saying is that let's say we have a proposition which is of this type. We're assuming some x belonging to alpha, and assuming that x, we can produce a proposition that depends on x. So basically, we are saying we have a general predicate depending on some x in alpha, and when we say that there exists an x such that some property is satisfied, basically when we want to say that there exists x such that p of x holds, what we actually want to do is first produce some a that has type alpha, and correspondingly produce a proof that p of a holds. Like p is the function. Basically, we want to produce a term of type p of a. So that's what we want to do over here. And so these are called dependent sums. These are analogous to Cartesian products in which the second coordinate can depend on the first one. So that's the idea over here. So I've written, yeah, so this is the correspondence. These are called sigma types as well. So let's say we have p, which is a function that assumes a and produces basically you can think of these as a set of types indexed by a certain variable of type alpha. So basically, to produce a dependent pair, we first give a particular a belonging to alpha, and we also produce a term of type pa corresponding to this a that we've chosen. So these are dependent sums. Correspondingly, we have the existential quantifier, which is basically saying that we take a certain a belonging to alpha, and then we also produce a term of type pa, which in other words is a proof of p alpha, a proof that pa is true. And together with these, we can construct a proof that there exists an x such that p of x holds. So this is complicated. This is implemented slightly complicatedly, and we can simplify the notation a bit. So this is actually syntactic sugar for what's going on behind the scenes. So what we actually have is a dependent function, which first takes in a term of type alpha, and another proof that p of alpha holds. And together with these, it produces a proof that there exists an x such that p of x holds. So yeah, so to prove this, we can. So I have an example over here saying that there exists an n such that n equal to n. This holds trivially for any n. We can choose one arbitrary, let's say 5. So we can say 5, and now we need to show that 5 equal to 5. This follows from reflexivity, so I'll just write RFL over here. So this is just to illustrate that uh, that existential quantifiers can be thought of as dependent types. So once I specify 5 over here, what I need to prove is that 5 equal to 5, and that depends on the first coordinate itself. So that's the correspondence. Uh, and so far we have seen the two major basically we have seen incarnations of the function types, which is one major type in type theory. Another very general family of types is what are known as the inductive types. So as you would have noticed, everything over here has the word inductive as a prefix, and these are all instances of a very general inductive type family. So I'll explain what these are first through an example, because the moment, like the first thing that comes to mind when the word induction is mentioned is probably the natural numbers. So the natural numbers might be a good place to start and motivate the definition of an inductive type. So what we have over here is that it's a very minimalistic syntax. So what we are saying is that natural numbers are defined using two constructors. The first constructor says that 0 is a natural number. The second constructor says that you have a successive function, which is of type naturals to naturals. So in other words, successor is a function which takes in a natural number and can and produces a natural number. So that's how inductive types are defined. And but this doesn't seem to capture all the properties of natural numbers right away, because if we contrast them with Peano's axioms, which are listed over here, we have 5 axioms and only 2 constructors to capture these notions. So uh, the reason this is the case is that the inductive type actually has a few general properties uh, from which these consequences follow. So the we've seen these 2 points already. The first two. The third one says that the successor function is injective, and the fourth one says that there is no number such that uh, basically zero is not the successor of any number. So that's what these two things say. But these are not explicitly stated in the definition that we saw of inductive, of the inductive definition of natural numbers. So we want to find a general property that we can state which captures these two as corollaries or as trivial consequences. So the approach that's generally used is essentially stating that uh, we are generating everything freely over here. So we have two constructors and we are generating things freely. So which means that uh, successor we assume that the successor function is injective. We don't assume any additional properties. We just assume that if we basically, if this was the case, then it would mean that some additional property holds that we are not aware of. The idea is that we just want to keep it simple. We are we are just treating this as like a freely generated set of terms. So we have zero, we have successor of zero, successor of zero, and there are no additional properties. So there's no extra things assumed, and there, yeah, basically this is captured in the slogan "No confusion." So that's the term that Lean uses to capture this property. So the in simple language, this is just saying that these are generated freely without any additional constraints. The most important property associated with the natural numbers is the property of induction. And we also need to find a way to generally capture this property of induction from just the constructors alone. So this is done in quite a clever way, and that's where inductive types get their name from. So the idea being that if we have two constructors, and like induction is basically we want to prove a property of the natural numbers, and a property of the natural numbers is essentially a function from the natural numbers to prop. To each natural number, we're associating a proposition, and we want to show that this is a valid function. Uh, and we want to do this stepwise. The idea adopted over here is that if we can prove that it's true in uh, each of the two cases specified, if we can prove it for the two constructors, then we can prove it in general for all natural numbers. So in other words, this means that we first need to prove that a property is true for zero, and we need to prove that the successive function preserves the true property. So if it's true for a certain if it's true for a certain natural number, then it's true for the successor of that natural number. And if it's true for these two constructors, then we can say in general that it's true for everything. So that's how the property of induction is captured. And for a slightly simpler example, uh, here's what's known as an enumerated type. What we're doing is we have a list of directions, north, south, east, and west, and this can be thought of as a set comprising 4 elements with just the fact that these are distinct. So if we want to construct a function that takes in a direction and outputs something else, uh, then we would do this by defining the function individually on each of these 4 constructors. So that captures the intuition of building a general function from directions to some other type by first defining it on each of the constructors. So basically the idea is that we are doing induction, and induction is analogous to doing recursion. So over here, uh, induction and recursion can be thought of as two sides of the same coin. Basically, when we're proving something by induction, we are essentially constructing a function from that type to prop. To each element of the set, we are associating a certain proposition, a certain type, which we want to produce a proof of. In recursion, we want to construct a type by uh, we want to construct a certain type by using the constructors repeatedly. We want to use simpler instances to build up more complicated ones. So that is the idea. And I will, so all these things over here used the inductive prefix. What we saw earlier were only the introduction rules. We saw how to construct a term of type and using and.intro, but we never saw how to use and.intro in and a term of type and pq in proofs. So this is captured by the recursion principle. And dot rec. Um, I think it's still loading. Yeah, there. Uh, so what this says is that if we have, if we can take a, if we basically if we produce a term, if we can construct a function from p to q to whatever thing we want to prove, then we can say that and proves that thing. And maybe this is more clear with or, I guess. I'll just a second. Um, so if we do this with or, several of the familiar details will drop out as consequences of this. So it says that if we can prove a certain fact by first assuming that it's true, by assuming that P is true, and then proving it, and then we can assume, we can, basically what we need to do is show that P implies the thing, and then we need to show it separately that Q implies the thing. With these two facts in place, we can show that the thing is independently true. So that's how OR works. And what we get is that anything trivially, any true statement trivially follows uh, from true. Basically, we already have a term of type true. We don't have to do anything there. And if we already have a proof of something, then we can just construct it trivially without doing anything. And with false, the thing for false is that if we have a proof of false, since false has no constructors at all, having a proof of false automatically implies anything, any other proposition. So all these facts sort of drop out as special cases of the the recursion principle on inductive types. And so inductive types themselves can be defined as being built from a small set of constructors. And if these constructors call upon previous instances of the type, they must be built up in a positive sense, which means that they depend only on simpler instances of the more general thing. And uh, like for example, in the case of uh, natural numbers are always built up from smaller natural numbers, and it's not the other way around. And the construction is also done freely with no additional assumptions. So in the case of natural numbers, we assume the free criterion means that the conditions 3 and 4 of Peano's axioms follow without any additional assumptions. And so this is how an inductive type is defined. And to create something that has an inductive type, we can use one of the constructors. And to use one of the uh, to use something that has an inductive type, uh, or to destroy it, we can use the recursion principle. So basically, what we're saying is that we have an inductive type over here with a bunch of constructors. We construct a function, or we construct a proof. We prove something by induction on this thing by proving it individually for each of the generators. So that is the idea over here. And so while so basically induction and recursion can be seen to be two sides of the same coin, because induction is the special case of a function that carries basically a function from that type to prop, and recursion is basically defining it more generally to any other thing. So the vector thing over here, the vector type that we saw earlier, yeah, so the vector thing was an example from natural numbers to uh, vector containing natural numbers defined using induction. And we can define other things using induction on natural numbers, other properties. So these are actually two sides of the same coin. They only vary in the target domain. So otherwise they're essentially the same. And these are unified in Lean. So to conclude, basically we have two major types of types, two major families of types in Lean. One are the function types, and the next is the inductive types. And remarkably, every single type in type theory can be constructed using just these. And moreover, we can express logic within the framework of type theory. So I'll just conclude by reiterating whatever I've said earlier. Uh, so type theory basically allows us to build a system of logic within itself, and it's also very rigid in checking errors. In a lot of cases over here, I didn't actually have to mention the type explicitly. It could infer it automatically from context. So that's another major advantage of type theory. And as a result, it has practical consequences in building theorem provers and proof checkers. So with that, I'd like to end the talk. These are the main references. Uh, the These are the two main references: the theorem proving in Lean manual, and another book called Logical Verification in Lean. Uh, these are some additional references. Uh, these two blogs are a very good resource for that I found uh, for learning the basics of type theory and so on. And yes, that's about it. Thank you. I can take questions.
Thanks a lot, Anand. It was an excellent talk. And
Thank you.
it was more than a glimpse into type theory, definitely. And like how you balanced the two things, like constructive logic and this together. So that was really good. Any questions for Anand?
I do have one. Thanks, Anand, for such a nice and informative talk. And my question is that you gave a very nice connection of type theory together with that constructive logic or intuitionistic logic. And also you mentioned that homotopy type theory is somehow the connection with the topology and this. So my question is that, is there exist any idea of type theory and its connection with geometric logic? Because geometric logic is the logic of topology or topos theory, let's say.
Unfortunately, I don't know anything about geometric logic, so I don't think I'll be able to answer that question. But I know that there are connections with category theory and so on. Like those are the connections that I'm aware of. But I'm not sure about geometric logic as such.
Any other questions? So I have one. So when you were discussing, like, what was that? Natural numbers is of type, then type is of type 1, and so on.
Yeah.
So is that similar to like the notion of universes, like Grothendieck universes or Von
Yeah, these are
universes?
called universals.
Okay.
So I don't know anything about Grothendieck universes apart from the fact that they're used in set theory as a remedy to Russell's paradox. So yes, in a sense, they are it's built this way for the purpose of avoiding Russell type paradoxes.
But only for, I guess, only for natural numbers. They are only indexed by natural numbers. Yeah, not beyond that.
Yeah, they're
Not
only like
indexed.
Yeah, they're yes.
Right. Okay.
How are Grothendieck universes indexed?
Using ordinals.
Okay.
Okay. Any other questions or comments? Okay, so we have had a great start for the student webinar series. So we also hope that everybody continues to encourage the students in future weeks.
And thanks, Anand.
Thanks, Anand. Yeah.
Thank you.
Yeah.
So hereby I declare that the talk is over. Yeah. If any informal chat is to happen, that can.
No, informally, very nice talk, Anand. Very well prepared.
Thank
Very
you.
well organized.
Thank you.
I'm going to stop the YouTube live right now.
Yes.
Okay.